fault analysis using Thevenin's theorem. Problem number 4. The diagram shows a generating station feeding a 132 kV system. Determine the total fault current, fault level and fault current supplied by each alternator for a 3-phase fault at the receiving end bus. The line is 200 km long. Take a base of 100 MVA, 11 kV for LV side and 132 kV for HT side. So the diagram is given. Generator 1 is of 100 MVA 11 kV, generator 2 is of 50 MVA 11 kV, and transformer 1 is 100 MVA 11 bar 132, and transformer 2 is 50 MVA 11 bar 132, and the corresponding reactances are given. And in the transmission line, we will be having two parallel transmission line of reactance X equal to 0.2 ohm per phase per kilometer. The total kilometer of the line is 200 km. At the end of the line, the fault occurs. So we need to determine the fault current, fault level and fault current supplied by the each generators. Solution. Step 1. First we need to divide the section in the single line diagram based on the transformer primary and secondary in order to find the reactance diagram parameters. So the first step, the transformer primary side is of section 1. Since both the transformer T1 and T2 having the same values in the primary, so we can divide the primary side of transformer 1 and 2 as common as section 1. And similarly, the secondary voltage is also same 132 kV for both the transformer. So we can divide the secondary side of transformer 1 and 2 as common as section 2. And the base value is given as 100 MVA and 11 kV base at the generator terminal, at the low voltage terminal. So we can select base kV as 11 kV at the low voltage side, that is primary side. And that is your section 1, the kV value is 11 kV. And base kV on section 2 is 132 kV, which is specified in the problem, and if it is not given, you can find using this formula. Base kV on HT side of transformer 1 equal to base kV on LT side of transformer 1 into HT voltage rating of transformer by LT voltage rating of transformer. You will be getting 132 kV. So this is your base values. Base MVA is 100 MVA, section 1 base kV is 11 kV, section 2 base kV is 132 kV. Now second step, draw the reactance diagram and find the parameters. So for this circuit, you can draw the reactance diagram. So per unit value of each component can be determined, and finally we can draw the reactance diagram and substitute the values. So first, to calculate the reactance for the generator 1, we can use this formula: Z per unit nu equal to Z per unit given into kV given divided by nu the whole square into VA nu divided by MVA given. So given value of the impedance is 15%, that is 0.15 here, and the kV given is 11 kV and the kV nu is at section 1 it is 11 kV, you can substitute, and MVA nu and given is 100 MVA since generator 1 has taken as a base value. So answer will be 0.15 per unit. Similarly, you can apply the same formula for transformer 1. The transformer 1 X value is 10%, so 0.1, and the primary side given kV is 11, and the primary side base kV is at section 1, that is 11. So you can substitute, and MVA is 100 for both given and the base value, and you will be getting 0.1 per unit. Similarly, for generator 2, 10% and 11 given, and 11 is base value, and 100 is the base value, and 50 is given in the generator for MVA. So you will be getting 0.2 per unit. And for transformer 2, X per unit nu equal to, for transformer 2 it is given X as 8%, so 0.08 into the kV given kV is 11 kV in the primary side, and the kV base nu is nothing but your base value that you can see from this box. The new value for section 1 is 11 kV, the section 1 is in the primary, and MVA nu is the base value which is 100 from this box you can take, and MVA given is, for transformer 2 the MVA value is 50 MVA, so you can substitute, you will be getting 0.16 per unit. And the feeders, a transmission line here, I will be having two lines are connected in parallel and both having the same values of X equal to 0.2 ohm per phase per kilometer. So in order to calculate the new value, you can use this formula: Z per unit nu equal to Z actual into MVA base nu divided by kV base nu the whole square. So Z actual is 0.2 ohm per phase per kilometer, so total kilometer is 200, so 0.2 is multiplied with 200, this is your Z actual, and into MVA base is 100 MVA and kV base is 132 kV, since this transmission line or a feeder is located at section 2, so section 2 base kV is 132 kV, so you will be getting 0.2295 per unit. And second feeder also having the same value, therefore Z per unit nu equal to 0.2295 per unit for the second feeder as well. Now the reactance diagram, you can draw the reactance diagram using the single line diagram. We will be having two generators. So for generator you need to draw EG value and followed by the reactance, and for generator 2 Eg value followed by the reactance, followed by the generator. You will be having a transformer T1 and transformer T2 here. Then after transformer we will be having a common bus bar. Then there will be a feeder, two feeders connected in parallel. Okay, at the end the fault occurs. Okay, so you can join these two lines. This is how you need to draw the reactance diagram. So this is the complete reactance diagram of the system, and we substituted all the values which we calculated, and now you can apply the Thevenin's theorem. So here it is a no load condition, the load is not connected, so IL is neglected, and no load voltage is not specified in the problem. So hence we can take V Thevenin, the Thevenin voltage equal to 1 angle 0, and we need to determine the Z Thevenin. Finally you have to find the fault current. So to calculate Z Thevenin, consider the reactance diagram, and this generator terminal you will be having the reactance 0.15 and transformer 1 is 0.1. These two reactances are in series. Similarly this 0.2 and 0.16 are in series. Okay, you can do series combination, you will be getting like this, J0.25 and J0.36. In this diagram you can say these two are in parallel and these two are in parallel separately. So you will be getting, after doing parallel combination, you will be getting this answer J0.1475, and here it is J0.1147. For parallel combination you have to do R1 R2 divided by R1 plus R2, that is J0.25 into J0.36 divided by J0.25 plus J0.36. you will be getting like this. Similarly you will be getting for the another term as well. And now these two reactances are in series, or both are in same line. These two are in series. Simply you can add these two, you will be getting the Z Thevenin, and you can add the V Thevenin equal to 1 angle 0. You will be getting the complete Thevenin equivalent circuit. So Thevenin equivalent circuit means whatever may be the complex electric circuit, you have to reduce that complex electric circuit into a single Thevenin impedance with a voltage source of Thevenin voltage. So here the V Thevenin is 1 angle 0 and Z Thevenin is 0.2622. So using this Thevenin equivalent circuit you can determine the fault current. So determine fault current. The fault current formula is IF equal to V Thevenin divided by Z Thevenin plus ZF, and Z Thevenin we determine, and ZF, the fault impedance is not specified in the problem, so you can substitute 0. You will be getting minus J 3.813 per unit, and this is your per unit value of fault current. Now the actual value of fault current equal to per unit value of fault current into base current. So base current can be estimated using this formula, MVA base into 10 power 3 divided by root 3 into KVB, where MVA base is 100 and KV base is 132, that is the fault location. The fault is located at section 2, the section 2 base value is 132. So you will be getting 437.38 ampere. Now you can substitute here to find the actual value of current. Actual value equal to per unit value of fault current into base value, that will be equal to minus J 1667.7 amps. So this is your actual value of fault current. Now step 5, determine the fault level. So to find the fault level you will be having a formula, fault level equal to per unit value of fault current into base MVA. So per unit value of fault current is 3.813 angle minus 90 or minus J 3.813, both are same, into 100 MVA, that is a base MVA, we will be getting 381.3 angle minus 90, or you can put minus J 381.3. Okay, so this is your fault level. And last one, step 6, determine current supplied by each generator. So here you will be having two generators or two alternators. The fault current we determine, that is 3.813 angle minus 90. So out of that, generator 1 supplies how much amount of fault current and generator 2 supplies how much amount of fault current, that we need to determine. So for that we can consider the generator part of the reactance diagram. So consider the generator side of the reactance diagram. In this reactance diagram we are going to apply the current division rule. So generator part of the reactance diagram, generator 1 reactance is 0.25, generator 2 reactance is 0.36. Okay, so base kV at generator side is 11 kV. So we need to find the fault current in per unit based on the generator base kV. So previously we determined the fault current in per unit based on the fault side base kV, but now we are going to find the fault current supplied by the generator. So generator side base kV is something different from the fault side base kV, since generator is located at section 1 and fault is located at section 2. Okay, so generator side base kV is 11 kV. So you have to find the base current, MVA base into 10 power 3 divided by root 3 into kV base, and this kV base is 11 kV. Previously we substituted as 132 kV in the fault side. Now it is in generator side, it is 11 kV. So you'll be getting the base current as 5248.6 ampere. And now the actual value of fault current will be equal to per unit value of fault current into base current. So per unit value of fault current already we determined, it is minus J 3.813 or J or 3.813 angle minus 90 into this 5248.6 will be getting minus J 20,012 ampere. And this is your actual value of fault current, that is a total current at the generator terminal. Now you can apply the current division rule and find the fault current supplied by each generator. Okay, so current division rule is current will be equal to total current into opposite resistance divided by sum of resistance. So here we will be having a reactance. So the total fault current into opposite reactance divided by sum of reactance. Okay, so for generator 1 we can find the fault current supplied by generator 1. So Ig1, it is a subtransient current, so Ig1 double dash equal to total fault current into opposite resistance. So we are concentrating on generator 1. So if you are going to find the fault current at generator 1, so this generator 2 is your opposite reactance. So total fault current into opposite reactance is 0.36 divided by sum of reactance. So you will be getting 11,810 angle minus 90. Similarly for generator 2, the total fault current is 20,012 angle minus 90 into opposite resistance. If you consider generator 2, the opposite resistance or opposite reactance is this J.25. So substitute this J.25 opposite reactance divided by sum of reactance J.25 plus J.36. So you will be getting 8201.6 angle minus 90. So this is the fault current supplied by the each generators.